All right, looking at the answers to the quiz questions, assuming that the presentation actually starts. I press the button for it to start. Okay, so question number 1. If I hit a material with a hammer and it squishes out rather than fracturing, then it is a blank material. I should have put A/and now, shouldn't I? And so, correct answer, Jessica?
Oh, hey, I got it right.
That was Jessica's question.
That's a quick question. Is it possible? I don't think I've used for a moment like that. Is that
Okay, sorry about that. Question number 2. Over here. Atoms are which one of these?
All of the above?
They are all of the above. They're microscopic. They're really tiny. They're mostly empty space. It's mostly that vacant space that was shown by the thin film experiment. This came from the same lecture as the one above. And they're made of protons, neutrons, and electrons. Noble gases. Where are noble gases on the periodic table? Because I saw Vanessa looking back there. Where are they? They're the ones that are on the far right, the group 18. And what is special about those?
They're radioactive.
Not all of them.
I don't know.
The bottom ones are radioactive. Top ones are not. They're inert. That's why they're called noble, because they stand alone.
Okay, well, I don't know what inert means.
We learned that. Inert means that it doesn't do anything.
Okay.
And finally, a car rusting is the result of which kind of change? Physical, chemical, elemental, or molecular?
Molecular?
Chemical.
Oh, yeah.
Chemical change.
Ooh, I only got 50, y'all.
Don't have to broadcast your scores. Okay, so the 2 types of change were physical and chemical. Physical change is where something that's a measurable property like density, color, transparency, changing from liquid to solid, those are physical changes. Chemical changes are changes where you actually are changing the chemical bonds. Chemical changes usually result also in a physical change, but if it has chemical change, we rule it a chemical change. So even though car rusting does have a physical change as well, it's a chemical change. All right, we're going to have one woo clap question, so I have this up here, but I'm going to move right past it rather than spending much time on it. So an ion. We've already learned the term ion and what it means, but I want to make sure we understand, because the first thing we're going to talk about today is ionic bonding, bonds between ions. So an ion is an atom that has either gained or lost electrons. So the example shown here is the example that we actually had for the last woo clap question last class period. On Friday, we had the question, if you take a sodium atom and that has sodium element 11, it said, and you remove 1 electron, then what atom does it have the same electronic structure as? And the answer we learned is illustrated right here. If you have 11 protons, then for a neutral atom, you should have an equal number of electrons, so you should also have 11 electrons. If you remove 1 electron, now you're down to 10. Looking at those dots for filling the shells, we're going to take away the highest energy electron, the one that's in the farthest out shell. And so this is the one that goes bye-bye. And we're left with the first 2 shells complete. And so the question then was, what looks like the first 2 shells complete? Neon has the first 2 shells complete. So that was the answer that we had when we had this question on Friday. So that's an ion. Because it lost an electron, what kind of charge does it have, positive or negative?
Positive.
Positive, because it has 11 protons and 10 electrons. 1 more positive. We call that a +1 charge. If it lost another electron, we say it's +2 because it has 2 more positives than negatives. But things don't have to be positive. They don't have to lose electrons. They can also gain an electron. So here's an example of an atom that gains an electron. This here has 9 protons. What element has 9 protons? I look back there too.
F.
F, fluorine.
Yeah. Heck yeah.
So we start with the fluorine atom. It's 1 electron short of having a complete shell. And one of the rules in chemistry is that atoms want to have complete shells. The sodium actually doesn't mind giving up its electron because that takes it to a complete shell. The fluorine really wants to grab an electron to fill that shell. And so the fluorine is likely to grab an electron from something, but that gives it an extra electron. So now it has a negative charge, and we would say this fluorine has a -1. The fluorine ion has a -1. So you notice here it actually shows those. On the left, it's just fluorine. On the right, it's fluorine with a 1-. Oftentimes, we don't write the 1 if it's just 1. We just put fluorine with a minus, and that's a negative ion. Here's an example of an ionic bond. Hydrogen. That H with a plus sign, what does that mean based on what we just did?
Oh, there's more like protons than...
There's 1 more proton than there is electron because it's just a single plus. Of course, how many protons does a hydrogen atom have?
1.
1. So how many electrons does it normally have?
2. Wait, 1.
1. Normally you would match.
Yes, yes.
So if it has 1 more proton than electron, it's lost its only electron. So that's actually a bare proton. Over here we have a water molecule. This water molecule, I actually put in a slide coming up on what a molecule is again. A molecule is multiple atoms. Actually, you can have monatomic molecules as well. Bound together. So this water molecule is already bound together. But we learned about electrical polarization. You took the balloons, you rubbed them on your hair, and you stuck them to the wall, remember? Still got them right there. We stuck those balloons to the wall because we were able to induce an electric dipole. That is, we were able to separate the positive from the negative charges. And in so doing, we made it so we could have an attraction between a charged object and the neutral wall. The same thing happens here. The hydrogens over here are plus 0.35, and the oxygen is a minus 0.7. So the oxygen is behaving like it's a negative 0.7 charge, not like it has 0.7 extra electrons. The hydrogen is missing an electron, and so we have opposite charges, a positive and a negative, that attract each other. And so we call that an ionic bond when it's a positive charge attracting a negative charge to hold the molecule together. And so these combine to form what's called hydronium. This ium means it's a positive ion here.
So an ionic bond is when a positive and a negative attract each other?
And that's what holds the molecules together, yes. So there's more than one type of bond, and that's the first type we're learning, when you have one's a positive ion, one's a negative ion. So this hydronium, notice that has H's and O's. Water has H's and O's. Hydrogen peroxide has H's and O's. That's why we need the prefixes like dihydrogen monoxide, if we're going to give the technical term for water, because both the H's and O's can have varying numbers. What would the standard name be for this hydronium ion? Hydronium is the common name. How would you name it with the standard name?
I don't remember. Hydrogen trioxide.
Actually, it's 3 hydrogens and 1 oxide. So it'd be trihydrogen. You had the right idea. Trihydrogen monoxide. Okay. So ionic bonds, here's another classic example. You know what would be more classic than this? If we change that fluorine with a chlorine. Because everybody knows sodium chloride. Do you remember our naming rules? Why is it sodium chloride?
Far left.
Okay, you start with the far left, so sodium comes first. and then you put an I on the end of the second one. So what would this be named if it's made from sodium and fluorine?
Sodium fluoride.
Sodium fluoride. The fluorine, because it's in column 17, it's in the halogens, it really wants an extra electron. So it grabs one and becomes an ion. The sodium being in column 1, the alkali metals, it is happy to give up an electron. So the sodium gives up electrons, the fluorine grabs electrons, you have opposite charges, they attract to each other and hold together. So that's an ionic bond. Here is showing the two held together by an ionic bond.
Good for them.
Good for them. Any questions about ionic bonds? Okay, take the silence as no, you understand ionic bonds.
Yes.
So, talking about molecules. Molecules, collections of 2 or more atoms. Now, here again, I said collections of 2 or more atoms. You can have a monatomic molecule. Those occur in the noble gases because they stand alone. Otherwise, they're not monatomic. So, most molecules are electrically neutral. The hydronium was not electrically neutral, but most are. And the molecule formulae, that's the formula you write for the molecule, has subscripts that say how many of each atom type are present. So water, H2O, H2 means 2 hydrogens, O, 1 oxygen. Hydronium, H3O, 3 hydrogens, 1 oxygen. Now the question here is, sodium sulfide is made from sodium ions. What's the charge of the sodium ion according to the screen?
Negative.
Plus, Na with the plus. Na is sodium. You may not know that. You always can look at the periodic table, but it's not going to have the word sodium on it. So that's the kind of thing that you actually need to connect. Na is sodium. And then sulfur, what is the charge state of the sulfur? Charge state, it's an ion with what charge? Negative what?
Negative 2.
Negative 2. Meaning it has 2 extra electrons. So what's the chemical formula for sodium fluoride? Well, I need to make it neutral. And since I have a plus here and 2 minuses there, my total charge, Q is actually the symbol for charge, is equal to plus 1 times the number of sodium. I'll put N, I don't know what to put here. I'll put A, plus minus 2 times B, where my formula is going to be Na with the subscript of A and S with the subscript of B.
Na2S.
Okay, now she's right. How did she get that? You know that has to equal 0. And you say, okay, since this is plus 1 and that's minus 2, if A is 2 and B is 1, then I would have plus 2 minus 2 equals 0, and it's a true statement. And so she's absolutely right. It's Na. You don't need to put the subscript 1. Or actually, you do need to put the subscript 2. S, you don't need to put the subscript 1. So we would just normally put Na2S. What about 4 and 2? 4 and 2 is just doubling, so it's still going to be true, but usually it's going to be the lowest whole number ratio. I say usually because there will be some cases where we'll see that's not true. Now, your woo clap question of the day. So what is the chemical formula for a neutral compound made of aluminum ions, that's Al3+, and oxygen ions, O2-. And remember, we're at woo clap. Okay, I'm sorry. Yes, now you can answer, and we have 1 of 4 answered. If you had answered previously, just answer again. It somehow timed out. I had reset it multiple times, but so that'd be okay. Thank you for all answering. We had 2 that said this and 2 that said this. So now we're just going to check using the formula we did on the previous. So for the top one that I'll do in red, Al has a +3 charge, so I'd have 3 times that +3 charge. O2 has a -2 charge. So 3 times 3 plus 2 times -2. What does that equal?
3 times 3 is 9. And 2 minus 2 would be negative.
2 times -2 is -4.
So 5.
That's not 0, but it needed to be chemically neutral. So that means that's not it. This one here, 2 times +3 plus 3 times -2, what does that equal?
6.
This first one's 6.
It's 0.
It's 0. It's 6 minus 6. This one here was 9 minus 4. So that means that this one here was the correct one because it was neutral. It said neutral compound. Anybody know what we call this neutral compound? Well, okay, that would be a correct name. Dialuminum trioxide would be a correct name. It has more common names. If it's a single crystal, we'll learn about crystals a little bit later, but crystal means that the atoms are in repeating positions. If it's a single crystal, we call it sapphire. If it's not in a single crystal, we call it corundum. So it has 2 different names depending on its state. This shows an aluminum oxide is the actual common name for it. Besides this is a gemstone name. Ruby is sapphire with an impurity. It has chromium impurities added in that give it the pink color. So ruby is a sapphire with impurities. And so this is actually how the bonds, lay out. And you probably have seen sapphire. Pure sapphire is transparent. It looks like glass. Now, that's our ionic bond segment. What's the key? What is an ionic bond?
If you look at the force and attraction between oppositely charged ions.
Okay, that's correct. Metals form what we call metallic bonds, which are a whole completely different beast. Metals, the things there in our transition metals, as well as we can have, some things there, I think, in the alkali metal and alkali earth metal. But mostly the transition metals, they have an electron structure that when you combine them, their valence electrons, remember the valence electrons are those outermost shell of electrons? Those valence electrons are actually held by the group rather than by the individual atom. So the valence electrons are just freely shared. It's like social.
Wow.
And so with those electrons freely shared, you can take one type of metal and another type of metal and you can mix them together and it just kind of shrugs. You're sharing your electrons, I'm sharing my electrons, we're all one happy family. And so with metals, they're actually held together by the shared electrons that they're all sharing. And you can easily mix in different metals. That's how you get different alloys. So alloy is a term for a combination of metals. So we have here a picture of a Sacagawea dollar. The Sacagawea dollar has a special alloy that's to make it so it looks like it's gold, but it's not gold. And so it's actually 77% copper, 12% zinc, 7% manganese, and 4% nickel to get that unique color that looks kind of like gold. So the alloys, you can easily mix different metals to create a metal with special properties. So we saw a picture in the previous lecture of a rusted out car. That rusted out car, what's it made out of? What elements is it primarily? Yeah, it's not aluminum.
Thank you, I couldn't think of the word.
It's iron.
That's right.
Iron rusts, but then you have your pots and pans that are made out of steel. What's the difference between steel and iron?
And the rest.
Okay, the steel is not supposed to rust. It's stainless steel. Unless you get cheap grade steel, like on our Maytag kitchen stuff, then the stainless steel rusts because they made it cheaply. What's the difference in steel and iron? Steel is an alloy of iron. It's mostly iron. But they mix in things like a little bit of carbon to help it to have different properties and to keep it from forming an easy oxide with oxygen to keep it therefore from rusting. Now we're shifting to a third type of bond. So what was the first type of bond? Ionic. And the ionic you're going to have to know a fair amount about. We'll come back and talk about more when we get finished with covalent. What was the second one? Metallic. The metallic you don't really need to know too much about other than knowing it's a special one where the electrons are shared by the whole thing. The third one is covalent. Covalent, remember the valence electrons are the outermost electrons, the ones that can participate in bonding. And covalent is when atoms share those valence electrons. So that's what the co is because they're sharing. Valence, the valence electrons. So an example of a covalent bond is shown here, two fluorine atoms. If it was ionic, what does fluorine want to do in terms of an ion? Does it want to grab an electron or lose an electron? What she's right. What does fluorine want to do in terms of electrons? It wants to grab an electron. Why? Because it's in that halogen column. It's one away from having a complete outer shell. And it's more stable if it can grab that electron and have the outer shell that's complete. So it wants to grab an extra electron. So the fluorine, as we saw before in the ionic bond example, had a -1 charge because it grabs an extra electron. Well, two fluorine atoms, if they're both minus charges, they're not going to be bound together. What do the same type of charges do? They have a minus and minus. What kind of force do they have?
Wait, minus and then repel?
They repel, that's right. So the two fluorines wouldn't bond if ionic bonding was the only option. But each fluorine wants to fill its shell, so what they do is they say, hey, why don't you come over here, and I'll share my electron with you, you share your electron with me, and we'll both pretend that we're complete. So you have, with our electron structures, as we learned before, fluorine has 9 atoms, 9 electrons, and it has 7 in the valence. So I'm just going to start at the top and put 7 electrons on my fluorine. 1, 2, 3, 4, 5, 6, 7. So remember, you just go around in a circle, 90 degrees for each one, and I ended up with 1 lone electron. Well, if I do that with another fluorine, so here's another fluorine, and obviously to make things match up, I'm going to start a different place. Now these two fluorines, each one has an electron that's by itself, and they say, hey, come on over, and we're going to share these two, so each one thinks it has 2 there. One that's it, and one that's its own, and one that is sharing from the other. And so this picture down here shows those put together, so this electron might go with this one goes with this one technically, but in practice they're shared. So covalent is very different from ionic. You're sharing electrons instead of transferring an electron from one to the other and then say, hey, now we're ions, let's get together. So the number of covalent bonds an atom can form equals the number of unpaired electrons. Fluorine had one unpaired electron, so it can do one covalent bond. Oxygen, just doing our same rule again. Oxygen 1, 2, 3, 4, 5, 6. That left me with two unpaired electrons, so it can form two bonds. And so water, you have H with one electron. Well, of course, that's unpaired. And so this will form a bond, and then you put another H with one electron. That forms a bond. And that's how you get two H's and an O bonded together by covalent bonds. The positions of the electrons don't exactly match what we did with our dot picture. You know why? Because atoms are three-dimensional, and my screen is two-dimensional.
I should hope so.
And so the bonds actually tend to be, well, imagine that my fingers are, yeah, I can't do it.
You don't
But-
have those little magnetic things that stick together for it?
Yeah, we use Tinker Toys, essentially, to simulate them, but it's going to have, each bond is, well, there's four directions that are as away from each other as possible, typically, and that gives you a specific bond angle here. It's, I think, 109 degrees between the two hydrogens. So, other examples, we have nitrogen. If you look at the periodic table, fluorine had 7 valence electrons, oxygen 6, nitrogen 5. So if you go around and do 5 electrons, you only pair up one pair, and the other 3 are unpaired. So nitrogen has 3 unpaired electrons. It will form 3 covalent bonds. And so ammonia has 3 hydrogen attached to it. Now, if you look at the shape of that ammonia, once again, because of the 4 sides, the 3 are going to essentially form a triangle, and the top is just going to have the electrons by itself. So if you look at this, if the top has the electrons by itself, what kind of charge do you expect to have up here in the top part of this molecule? If it has 2 electrons up above everything,
Positive?
you'd expect a negative because of those 2 electrons. Right. The very
But 2 negatives equal positive. Like when you add them together.
no. Two negatives in the English language. Or if you multiply them, they do. But when you add them, -1 and -1 is -2. So the top behaves as a negative. The bottom with the hydrogen ions appears as a positive. Ions, they're not ions, but. And what happens now is we have something just like with water that has a negative side and a positive side. So if a hydrogen ion comes floating by, it says, ooh, that's the opposite charge, and it will snap on as an ionic thing and give you ammonium. Whoops, I thought I had ammonium on the next slide, and I don't. So if you add a 4th hydrogen, so if you do NH4, it's going to have a plus charge because you did it by bringing in a hydrogen ion, not a hydrogen atom, and that's called ammonium. And you're wondering, why are these important? Once again, in the lab, we're going to see these things. So having at least seen the name helps you to understand more what you're working with. And of course, we like to use ammonia cleaners in our house. And so it's a common household chemical. Last example, I think, is methane. Methane is this thing on the right. Carbon, if you take carbon, we're going one more to the left. We now have 4 valence electrons. So 1, 2, 3, 4. Each one is unpaired. It can form 4 covalent bonds. And so if we form covalent bonds with hydrogen, it doesn't have to be hydrogen. We've just been using hydrogen because it's convenient. If it forms 4 covalent bonds with hydrogen, then you have CH4. What would the standard name be for CH4?
What's
Go ahead. What's your question first, Alex?
Tetra.
Okay.
Um,
But let's start with our first
Wait,
rule.
what?
We take the one that's leftmost on the periodic table. Which one's to the left? The hydrogen. So we're going to have hydrogen first. Then we'll go with our prefix, which is what Alex was saying. Tetra, hydrogen. Carbide, because we changed the ending to I. So tetrahydrogen carbide would be a technical name. We actually should probably say monocarbide. Just move that over. Monocarbide, because that was a mess. I forgot, different program, different rules. Because there's a whole category called hydrocarbons, atoms made up with different numbers of hydrogen and carbon. So you have to be specific about all the numbers. But its common name is methane. So methane is CH4. And by now you should have figured out how the covalent bonds are working there in the methane. Now, we talked previously about the ozone layer, I think, and about chlorofluorocarbons. You recall talking about chlorofluorocarbons? No. Maybe it was my other class then. Well, we used to use compounds that were similar to methane, but they had chlorine and fluorine. Because if I have chlorine, how many valence electrons does the chlorine atom have? How many valence? It's 7, you're right. How many valence electrons does the atom chlorine have? And you look back at the periodic table and you just say, okay, we're only counting groups 1, 2, 13, 14, 15, 16, 17, 18 in valence electrons. And so looking at those, you have sodium, magnesium, aluminum, silicon, phosphor, sulfur, and then chlorine. It's a total of 7. It has 7 electrons in its valence shell. So I'm going to put my 7 in. I'm going to start here for convenience. 1, 2, 3, 4, 5, 6, 7. So there's my dot structure for the chlorine. It has 1 lone electron. It can bond covalently with one of those carbon electrons. And likewise, I could have a chlorine over here. There we go. 1, 2, 3, 4, 5, 6, 7. And these would bond. And then I will put a fluorine here. 1, 2, 3, 4, 5, 6, 7. Fluorine also has 7 because it's in the same column as chlorine. And these bond, and I can do the same up here. And of course, I don't have space for the top ones because I didn't give myself space. And so you can form a molecule that has fluorines or chlorines in the place where we had hydrogens. And it's still forming those covalent bonds. Here's a more complicated covalent structure. What's more complicated about these pictures than what we saw before?
They have more color.
Well, that's true.
Which means, yeah, I was gonna say there's a lot more bonds.
There's more bonds. It has 2 lines between them, here, here, and here. It has 3 lines here. So how does that work? Well, if we take the oxygen once again. I'll start here. 1, 2, 3, 4, 5, 6. There I have oxygen complete. If I do another oxygen, 1, 2, 3, 4, 5, 6. Now we can see that these can pair up and these can pair up. And so that forms a double bond. it has two situations of sharing electrons with each other instead of just one. Now, that's easy enough to draw. I just had to rotate my oxygen molecules a little to make it work. For the nitrogen case, you have 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. These bond together, these bond together, and these bond together is the only way you can really draw it. It has 3 pairs of electrons being shared between the 2 atoms. So that gives it the triple bond. Of these bonds, do you expect triple bonds to be stronger or weaker than single bonds?
Stronger.
Yeah, I expect it to be stronger. I believe that is also correct.
Oh, that's good.
Yeah. We've talked about what's called the Lewis dot structure. What we've been doing is called the Lewis dot structure, showing those dots and showing how the covalent bonds occur. We only use Lewis dot structure for covalent bonds, not for ionic bonds. What's the reality of a covalent bond? I said the electrons are shared, so the picture on the left is the Lewis dot structure for a hydrogen molecule. Hydrogen molecule, 1 electron from one hydrogen atom is shared with 1 electron from the other hydrogen atom. They're both happy. The picture on the right is the reality of the situation. These electrons don't just sit here, right? The Lewis dot structure is a little deceiving if you think that's where the electrons are. The electrons are hanging out around the atoms, and so we have a symmetric distribution for the case of hydrogen, where the electrons sometimes are going to be over here, sometimes here, sometimes here, but the number of dots indicates how likely it is to be found if you make a measurement. Where are you most likely to find the electrons in a hydrogen molecule? Just looking at the picture. Where do you have the most dots? In the middle. So you're most likely to find the electrons in the middle, but you could find them anywhere around this roughly dumbbell-shaped molecule. Now, what's the difference between a hydrogen atom and a hydrogen molecule?
Atoms are what make up molecules.
Atoms make up molecules. A hydrogen atom is a single, non-bonded thing.
And molecules are bonded together.
Molecules are bonded together. So a hydrogen molecule is H2. Correctly.
The Lord is blessing today. It's his 4th cup of coffee.
So the hydrogen molecule has 2 hydrogens, whereas the hydrogen atom has just 1. The hydrogen molecule is written as H2 because we use the subscript to indicate how many of that atom. Yes.
Oh.
What's the difference in the hydrogen molecule and this one here? What would the name be for HF? Hydrogen fluoride. What's different about this picture?
Noticing there's a lot on the right side of it.
Yeah, it's not symmetric anymore. With the hydrogen molecule, it was symmetric because the hydrogen atoms were just the same. Now with the hydrogen fluoride, the hydrogen doesn't get as much electron as the fluorine does. There's a lot more dots around the fluorine than there are around the hydrogen, so it's not equally shared anymore. The fluorine grabs more. Why?
It's selfish.
It's selfish. That is perfectly correct. The fluorine atom has a greater electron affinity. The electron affinity is how strongly an atom wants an electron. The fluorine really has a strong electron affinity. It really wants extra electron.
Is it sentient?
No, it's not.
This?
I know, I'm anthropomorphizing my. The hydrogen, on the other hand, it's kind of ambivalent. It's good, but I can go without it. And so the fluorine says you can go without it, and I would like it. It grabs as much of the electrons as it can. So this ends up with what we call a polar covalent bond. Polar, because the charge is not evenly distributed. Think back to a couple chapters ago in the physics section, we talked about electric charge, and we had polar things. And it was on the test, right? You have the charge is not symmetrically distributed. It's more on one side, positive, and more negative on the other side. So this is a polar covalent bond. Now, the side that has more electron is the negative side. The side that has less is the positive side. So here's where I introduced that term electronegativity, the ability of a bonded atom to pull on shared electrons. So the term the textbook uses is the pulling power for the electronegativity, how strongly it will pull an electron. And electronegativities, this chart shows you electronegativities of all of the elements. Well, not all of them because it's skipping everything after actinide in the seventh period. 1, 2, 3, 4, 5, 6. Yeah, seventh period. But the thing you should note is down here at the bottom left corner, francium 0.7. That's a fairly small number. Up to the top right, fluorine 3.98. Fluorine has a very strong electron affinity. It really wants electrons. Francium has a very low electron affinity. It's cool without having extra electrons. It can give up its electron just fine. As a general rule, just like with sizes, in fact, for the same reason as the sizes, the lowest electron affinity is the bottom left corner. The highest electron affinity is the top right corner, not counting the noble gases. The noble gases being inert, their electron affinities are 0. They don't want an extra electron. They also don't want to give up an electron. They're just happy the way they are. They're not selfish.
That's good. They're just fighting.
So notice fluorine is the most electronegative. It's the thing that is the most likely to grab electrons from anything it can. And so we use fluorine in a lot of our examples. Hydrogen is somewhere in the middle. Notice fluorine, it's essentially 4. Hydrogen, 2.2, about half of that. And then if you go down below hydrogen, everything else in the alkali metals has a very low electron affinity. Hydrogen, the reason its number is bigger than all the rest in the first column is because it would be equally correct to write the periodic table with hydrogen right here. It'd be correct to write it in both places because hydrogen has 1 electron in its valence shell, and it's 1 electron short of having a complete valence shell. And so you will actually find some periodic tables that show hydrogen in both locations. And so if it was over here on the right, its electron affinity would be over 4, right? Just following the pattern. On the left, its electron affinity would be about 1, and its actual value is somewhere in between because it's really both. That is both. It can give up, it wants an extra electron, and it doesn't want the electron. It has both of those natures. This is another thing that you're going to have to know about. You're going to have to be able to answer questions like, where do you have the highest electron affinity? Where do you have the lowest electron affinity? Highest electron affinity, top right corner, not counting the noble elements. And that's why the smallest atoms are the top right corner, because they have the strongest force pulling things in. Indicating polarity. Sodium fluoride. Is it time for me to quit? 2 minutes. Sodium fluoride is an ionic material. Why is it ionic? Hydrogen fluoride is polar covalent. Fluorine is non-polar. So how do we determine these? If you have the electronegativity difference between the two participants is greater than 2, then we call it ionic. Everything really is somewhat ionic and somewhat covalent. So these are somewhat arbitrary in description, but you need to know these in the homework. Well, not the homework that's due on Wednesday, I don't think, but on the homework that's going to be due the following week, you're going to have to do some examples of determining if bonds are covalent, polar covalent, or non-polar covalent. So looking at this, for sodium fluoride, sodium is 0.93 for its electronegativity. Fluorine is 3.98. So for sodium fluoride, you have 3.98 minus 0.98 equals 3. The difference in electronegativity is 3. If this is bigger than 2, then it's ionic. Now, which side is going to be positive? Which element lost its electron, sodium or fluorine? Sodium. So the sodium side is positive. So in our picture, we have a plus here on the sodium and then an arrow going to the negative side, indicating which side is positive, which side is negative. It's ionic because the difference in electronegativity was greater than 2. Yes, Alex?
Have you posted the homework?
Yeah, I posted it last week.
Is it not true that the one on the right is always positive?
That's only true for these pictures. You can have them arranged however you want, so it's not always going to be that way, I don't think. It probably will be, actually, but the fluorine, by definition, if you have two of the same atom, they have the same electronegativity. The difference in electronegativity is 0. And if it's between 1.6 and 0.5, then it's a polar covalent. So if we were to calculate for H and F, we would see that for HF, the change in electronegativity is equal to, well, 3.98 minus 2.2 is equal to 1.78. 1.78? Is that right?
6. Oh, just kidding. I'm sorry, I thought you had a different mark.
Yeah, that should be 1.78. 1.78 would actually be over here. Okay, it is now time for us to end class. Have a great Monday.
Thank you.
You are welcome.